This is Lecture 1G for Calculus 1, Piecewise Functions. Piecewise functions are common in almost any discipline that you're planning to go into. For example, if you were, say, working in field biology and you were counting fish at a weir, you would have one function that might describe the fish as the counts of the fish that you have over, say, a couple of weeks. If a run suddenly comes through, that graph is going to change drastically. That piece of data there would be represented by another function. Together, they would make up a piecewise function. Electrical engineering is full of piecewise functions. Every time you switch out a battery or you switch in a load, the output from the circuit changes dramatically. That would also be represented by a piecewise function. Here's what piecewise functions look like mathematically. Say I have a function, I'll call it g of x, and I'll let it be represented by this linear function, 3x plus 6. If nothing else is stated, its domain is all the real numbers. There is nothing to prevent a number from being multiplied by 3 and having 6 added to the result. But if after that I specify that x can only vary from -2 to 4, then the domain of this function g of x is restricted to this closed interval -2 to 4. When I go to graph this function, I can only legitimately draw it between x equals -2 and 4. So I'm going to do that now. First, I would look at the value of g at the endpoints of its domain. When x is -2, put that in the equation, you find that g of x is 0. So right here, I will put a dot, try to put a solid dot here, at -2 and 0. That would represent the point of g at the lower endpoint of its domain. Then I look at g at the upper endpoint of its domain. In that case, x is 4, and I find that g of 4 would be 18. So at 4 and 18, I would again put a solid circle. To draw the function, I then just connect these two dots. Okay, that is the function g of x, x restricted to -2 to 4. Now say I have another function, h of x. It's also a linear function. Right here. Okay, and again, with no specifications, you can assume that its domain is all real numbers. Actually, you shouldn't assume it. It should always be written, but by convention, we usually don't state it if it's all real numbers. But if then I go along, just like I did for g, and I restrict the domain of h to be 4 to 6, an open interval at 4, and then having open and closed at 6, then I have restricted the domain to this half-closed interval 4 to 6. Again, I can only legitimately draw h between 4 and 6, and I'm going to do that now. Okay, first I'm going to look at it at the lower endpoint of its domain, which is 4, and find that at that point h is 18. But since 4 is not included in the domain, I have to draw that point with an open circle, and I'll do that right here, an open circle. Okay. Now I look at h at the upper endpoint of its domain, which would be 6, and find at that point h of 6 is 6. So I can go over here, and at 6 and 6, I would put, in now this case, a closed circle because it is closed at 6. So here's my closed circle. And now if I want to draw that, go and get the line here, I can draw a line between these 2 points. That's still an open circle over there, even though it got kind of closed in. Okay, that's my graph of h. I can have the graph of h be nowhere else on the Cartesian coordinate system. It's possible to put both of these functions on the same graph. I would do that by adding the graph of g to the graph of h, and I'll do that right here by taking my point at -2 and 0 and connecting it up here to the point at 18 and 4. In this case, there was a closed circle from g of x because 4 was included in its domain. The closed circle supersedes the open circle, and here would be your graph. Okay. If you just had this graph by itself, you could try to represent it by some kind of complicated polynomial. On the other hand, you could say, okay, it's a line here, and it's a line over here. Let me just represent it as the 2 lines that it is, put them together, and call that a piecewise function. And here's how you would write the piecewise function. Note that right here at the top, at the first piece, here was the g of x, and it's right here. I specify the function, and I specify its domain. That is the first piece of the piecewise function. On the second line, I specify the second piece of the piecewise function. There's no overlapping. 4 is not common to both of them. Each one was a function. F is also a function. And here's what it would look like. It's just as I tried to draw it a few minutes ago. So here's your first piece. Here's your second piece. It is a continuous piecewise function. It doesn't have to be continuous. This one just happens to be continuous. The domain of F is the closed interval from -2 to 6, but each piece has its own subdomain. -2 to 4 for the first piece, and from an open interval at 4 up to 6 for the second piece. Okay, now I'll give you an example from real life so that you don't think I'm making this up. Here is the charges. You can get this off the website for Homer Electric, and these are the residential electric charges north of Kachemak Bay. Everybody who's on the grid pays an $11 charge. Then the energy charge is broken into two pieces. For the first 800 kilowatt hours, you pay $0.12718 per kilowatt hour. If you go for every kilowatt hour over 800, you have a slightly reduced rate. So now I'm writing this as a piecewise function. The piecewise function, I'm going to call it C, give it one name. I write this curly bracket here. Then here's the $11 charge. Let me get the highlighter. Here's the $11 charge. Okay, have to pay that. Then here is my rate if I use less than 800 kilowatt hours per month. Okay, what happens if I go over 800 kilowatt hours per month? Well, I still had to pay the $11 charge. Then I have to pay this $101.744 for the first 800 kilowatt hours that I used. Everything above that, I'm now paying at that reduced rate, and you see I've restricted the domain of this function to be greater than 800 kilowatt hours, the domain of the first piece to be less than or equal to 800 kilowatt hours. And here's what a graph of that would look like. So here you see the rate. You can see that the slope going from the $11 charge at one end all the way up to your $800. Here's your $800. So this whole area right through here is if you use less than 800 kilowatt hours per month. If you use more, you had to pay for the first ones, the first 800 kilowatt hours. You had to pay for the $11 fee, and then you can see that the slope along this line is less than, let me get an arrow here. The slope here, that's some arrow. Okay, didn't want to draw an arrow. Let me go get it here. So you can just kind of check. Okay, that's not working. Well, you can see that the slope here is less than the slope there, which is what you expect since you were paying a little less for your usage over 800 kilowatt hours. Here's a second example for the metered water service for the Kenai Borough. The price that you pay is $1.21 per 1,000 gallons of water, and you pay that as a minimum charge up to 15,000 gallons per month. So if you don't even turn the water on, you have nothing running, you're still going to pay for 15,000 gallons a month. And that will give you a minimum charge of $18.15. After that, you start paying for every 1,000 gallons that you're using. I'm going to write this as a piecewise function. Here's the water cost. The first piece of it right here is the $18.15 that you pay all the way up to your usage of 15,000 gallons per month. Okay. After that, you just start paying for it. $1.21 a gallon, 1,000 gallons. This makes another piecewise function. Notice that the first piece is a constant, and that's perfectly acceptable. Notice also that the domains do not overlap. Each one is a function. C is also a function. And here's a graph of the water charges. You can see right here that here is your flat rate up to 15,000 gallons. After that, you see the slope. And so there's a sudden drastic change. These are two pieces graphed on the same graph. They are the same function. Okay, so far what I showed you were linear functions. Piecewise functions do not have to be linear. Here's an example using an exponential. So this is the charge Q on a capacitor. All right? on the first piece from 0 to 5 seconds, you happen to be charging this capacitor up to 10 coulombs, whatever your units are here. And this is the function that describes it. Okay. At 5, you throw a switch. You cut at the battery and you start to discharge that capacitor. So now you have this first part of the function right through here is the same as the charge that you'd build up during your charging cycle. The next section of the function, the e to the minus t minus 5 over 2, is the discharge. They are proceeding at different time constants. And I'll show you what that. Okay, so here's a graph of that capacitor being charged up right through here. This part is the charging cycle. At 5 seconds, you throw the switch and you start to discharge the capacitor. So this is a continuous function, okay, but it is not linear, and that's perfectly acceptable for a piecewise function. But the piecewise functions don't have to be continuous. This is just a little plot. It has nothing to do with anything physical, but this is a discontinuous function. Okay. So the domain of this function is minus 1 to 3. It consists of one piece, looks like y equals x, from minus 1 and 1 up to 0. So here's the first piece of the function. Then you have something which, it's not parabolic, I don't know what it is, starts at 1 and goes to 2, but its domain does not include the point 1, x equal 1. At 1, you start a semicircle. So the semicircle goes from 1 all the way up to, we're at 2, which looks like it might have had the value 1. At that point, you have the one point at 1 now set equal to 0. That will give you, so far we've got 1, 2, 3, that's the fourth piece, and then the fifth piece is just the rest of the semicircle. So that's just an example of a discontinuous piecewise function. Okay, so here's a little summary for piecewise functions. Just to be familiar with them, they are very important and they occur frequently, especially in calculus. To draw a piecewise function, always and first evaluate each piece at the endpoints of its little subdomain. That's where it's going to live. Find out where it is at the beginning and ending of that domain. If it's a open or half open interval, draw that point with an open circle. If the interval is closed, draw that point with a closed circle. Closed circles override open circles. Since each piece is a function, and the domains do not overlap, so you have no closed circles on closed circles, the result, this piecewise function, is a function.